Welcome to today's paper reading. Today's paper is titled, CAT3D, Create Anything in 3D with Multiview Diffusion Models. This paper was published on the AR14 preprint by Ruiqi and colleagues from Google DeepMind. The abstract introduces CAT3D, a novel method for 3D reconstruction that simulates the real-world capture process using a multiview diffusion model. Unlike traditional methods that require hundreds to thousands of images, CAT3D can generate highly consistent novel views of a scene given any number of input images and target viewpoints. These generated views serve as input for robust 3D reconstruction techniques, enabling real-time rendering from any viewpoint. Notably, CAT3D can create entire 3D scenes in as little as 1 minute, outperforming existing methods for single-image and few-view 3D scene creation. For more results and interactive demos, visit the project page at cat3d.github.io. Figure 1 illustrates how CAT3D facilitates the creation of 3D scenes from any number of generated, or real images. The process involves utilizing a multiview diffusion model to generate consistent novel views of the scene. These generated views are then used as input for robust 3D reconstruction techniques, resulting in 3D representations that can be rendered from any viewpoint in real time. CAT3D significantly reduces the time required for 3D scene creation, outperforming existing methods for single-image and few-view 3D scene creation. The demand for 3D content is growing due to its importance in enabling real-time interactivity in applications like games, visual effects, and wearable mixed reality devices. Despite this high demand, high-quality 3D content remains relatively scarce. Unlike 2D images and videos, which can be easily captured with consumer devices, creating 3D content requires complex specialized tools and a substantial investment of time and effort. Recent advancements in photogrammetry techniques have made it easier to create 3D assets from 2D images, but creating detailed scenes still requires a labor-intensive process of capturing hundreds to thousands of photos. This often leads to incorrect geometry and appearance if the scene coverage is insufficient. The research builds on the concept of 2D priors for 3D generation, where text-to-image models provide a generative foundation. This approach often requires an iterative distillation process to create coherent 3D models. Multiview priors offer a stronger consistency check for 3D content, leading to higher quality and more efficient 3D extraction. Video priors, while capable of generating realistic videos, present challenges in exact camera control and 3D generation, necessitating specialized fine-tuning for better results. CAT3D employs a two-step approach for 3D creation. First, a multiview diffusion model generates a large number of novel views consistent with input views. Second, a robust 3D reconstruction pipeline processes these generated views. This decoupling enhances computational efficiency and reduces complexity. The multiview diffusion model is trained on single or multiple views to generate multiple output images, utilizing camera pose embeddings. For 3D reconstruction, the model improves robustness by incorporating a perceptual loss and weighting losses based on the proximity of generated views to observed views. Figure 2 showcases the capabilities of CAT3D in creating high-quality 3D objects or scenes from various input modalities. The first 2 rows demonstrate the process using an input image generated by a text-to-image model. Rows 3 to 4 illustrate the results from a single captured real image, while the 5th row shows the outcome from multiple captured real images. This figure highlights CAT3D's versatility and effectiveness across different input types. Figure 3 illustrates the CAT3D method for creating a 3D representation of a scene from one to many views within a minute. The process involves 2 main stages. First, generating a large set of synthetic views using a multiview latent diffusion model conditioned on input views and target camera poses. Second, running a robust 3D reconstruction pipeline on both observed and generated views to learn a NERF representation. This approach decouples the generative prior from the 3D reconstruction, leading to computational efficiency improvements and reduced methodological complexity compared to previous methods, while enhancing image quality. Figure 4 presents a qualitative comparison of view reconstruction on scenes from the Martin-Brualla F360 and CAT3D datasets. The samples are rendered images with 3 input captured views. The comparison highlights that CAT3D aligns well with ground truth in seen regions, while also successfully hallucinating plausible content in unseen regions, a feature where baseline approaches like reconfusion often fall short. The experiments in this study were conducted using 4 datasets with camera pose annotations, Objaverse, CAT3D, Real Estate 10K, and MVIMGNet. The CAT3D model was evaluated on 2 main tasks: view 3D reconstruction and single image to 3D generation. The results demonstrate significant improvements in both qualitative and quantitative metrics compared to previous methods. CAT3D achieves state-of-the-art performance across various settings, reducing generation time from hours to minutes. Additionally, the model produced higher resolution results with better detail preservation, particularly in unobserved regions. Table 1 presents a quantitative comparison of view 3D reconstruction methods, highlighting CAT3D's superior performance. CAT3D achieves higher PSNR, SSIM, and lower PIPS scores compared to baseline methods like SIPNRF, 0NVS, and reconfusion. Notably, CAT3D shows significant improvements on challenging datasets such as CAT3D and Martin-Brualla F360. Additionally, CAT3D significantly reduces the generation time from 1 hour to just a few minutes, making it a more efficient solution for 3D reconstruction tasks. Table 2 evaluates the quality of image to 3D conversion using clip image scores. It highlights that CAT3D achieves competitive results compared to object-centric baselines, such as ImageDream and IM3D, while also demonstrating its capability to work on whole scenes. The table provides quantitative data on the performance of CAT3D in relation to these baselines, showcasing its effectiveness in preserving image quality during 3D conversion. Figure 5 illustrates the process of creating 3D models from single input images. The middle row showcases the 3D models generated by CAT3D, which exhibit higher quality compared to the baseline methods shown in the bottom row, particularly for scenes. For objects, CAT3D's renderings are competitive. The scale ambiguity inherent in single image inputs significantly amplifies the differences in the renderings produced by different methods. CAT3D is a unified approach for creating 3D content from multiple input images. It uses a multi-view diffusion model to generate consistent novel views of a 3D scene, which are then processed through a 3D multi-view reconstruction pipeline. This approach decouples the generative prior from 3D extraction, resulting in efficient and high-quality 3D generation. However, CAT3D has limitations. The model is trained on datasets with constant camera intrinsics, making it less effective with varying intrinsics in test cases. The generation quality also depends on the expressivity of the base text-to-image model, and it struggles with out-of-distribution scene content. Additionally, the multi-view diffusion model supports a relatively small number of output views, which may not all be 3D consistent. Future work could explore initializing the multi-view diffusion model from a pre-trained video diffusion model, increasing the number of conditioning and target views to improve consistency, and automating the determination of camera trajectories for different scenes. Thank you for watching.